Chapter 3, Basic Aerodynamic Theory. So the principle of continuity. One of the fundamental laws of the universe is energy and mass can neither be created nor destroyed, only changed from one to another. To demonstrate the effect this basic principle of continuity as an aerodynamic theory, it is instructive to consider a streamlined flow of air through a tube which has a reduced cross-sectional area in the middle, so reduced space. The air mass flow, or mass per unit time, so kilograms per second, for example, through the tube will be the product of the cross-sectional area, which is represented by the letter A, the airflow velocity, V, and the air density, rho. Mass flow will remain a constant value at all points along the tube. So the equation of continuity is A times V times rho equals a constant. So what this means is that the mass flow of a certain amount of kilograms per second will remain constant even when the cross-sectional area is lower, for example in this part here. Because air is a compressible fluid, any pressure change in the flow will affect air density. However, low subsonic speeds, less than 0.4 Mach, density changes will be insignificant and can be disregarded. So the equation of continuity can now be simplified to A times V equals constant, or velocity equals this constant over the area. So the simplified equation will be the cross-sectional area times the speed and equals a constant. So the constant is the mass flow, kilograms per second. And now we can do the speed is equal to this constant of kilograms per second divided by the cross-sectional area. So as we can see here, this is the mass flow constant. So 52 kilograms per second, always, divided by the area, and we'll give you different speeds. So as we can see here, if we divide this 52 kilograms per second divided by 0.5, and so here is less than 1 meter squared, the air has to accelerate in order to maintain a constant of 52 kilograms per second. So it gives us 104 meters per second. And here goes back to this original 52 meters per second. So the principle of continuity. Because the mass flow must remain constant, it can be seen from the equation of continuity that the reduction in the tube's cross-sectional area results in an increase in velocity, and vice versa, as we were just stating a second ago. The equation of continuity enables the velocity changes of airflow around a given shape to be predicted mathematically below 0.4 Mach. Now, Bernoulli's theorem. In the steady flow of an ideal fluid, the sum of the pressure and kinetic energy per unit volume remains constant. So an ideal fluid is both incompressible and has no viscosity. This statement can be expressed as pressure plus kinetic energy equals constant, or pressure plus half rho times square of speed, which is the kinetic energy. This is the formula for dynamic pressure. So let's consider a mass of air. Static pressure 101,325 newtons per square meter, a density of 1.225 kilograms per cubic meter, and the velocity of 52 meters per second. Its dynamic pressure, this one, will be 1,656 newton per square meter. Applying this equation, dynamic pressure equals alpha of the density, which is this one, times speed square, speed and speed. So this is the pressure, which this is the same as saying 1013.25 hectopascals, but it can be said as well as 101,325 newtons per square meter. So this is the pressure. The kinetic energy of this air, so the dynamic pressure, okay, so that's the static pressure, dynamic pressure, equals a constant of 102,981 newtons per square meter. So this is the constant value of the newtons per square meter that this air is applying. So as we can see here, static pressure and dynamic pressure, and they always have to give the total pressure of a constant. So as we can see here, in order for the total pressure to remain constant, something has to change in dynamic pressure and static pressure. So dynamic pressure increases, so speed, dynamic pressure increases, and static pressure now here decreases, so there's a decreased static pressure here. So this is the lift because of this acceleration in dynamic pressure. So Bernoulli's theorem, because the velocity of air at the throat has doubled, its dynamic pressure has risen by a value of 4, and the static pressure has decreased, as I was just saying. The significant point is that static pressure plus dynamic pressure is a constant. This constant can be referred to either as total pressure, stagnation pressure, or pitot pressure. So this is the total pressure or pitot pressure that we were talking about in the previous chapter. Total pressure was static pressure plus dynamic pressure. It can be seen that flow velocity is dependent on the shape of the object over which it flows, and from Bernoulli's theorem it is evident that an increase in velocity will cause a decrease in static pressure, and vice versa. The tubes illustrated above are used only to demonstrate the principle of continuity and Bernoulli's theorem, and is of no practical use in making an airplane fly. But an aerodynamic force to oppose the weight of an aircraft can be generated by using a specially shaped body called an airfoil. This is an airfoil, typical airfoil section. The airflow velocity over the top surface of a lifting airfoil will be greater than that beneath. So the pressure differential that results will produce a force per unit area acting upwards. The larger the surface area, the bigger the force that can be generated. So here we can see same stream tube, but in the opposite. So there's a cross-sectional area that is smaller than the other two parts. So streamlines and the stream tube. A streamline is the path traced by a particle of air in a steady airflow. So these are all particles of air, and the way they follow. And streamlines cannot cross, so they can never cross each other. When streamlines are shown close together, it illustrates increased velocity, such as here. So here, they get squeezed together, so they go faster. And vice versa, so here they're decreasing, the speed is decreasing. Diverging streamlines illustrate decelerating airflow and resultant increase in pressure, and converging streamlines illustrate an accelerating airflow with resultant decrease in pressure. Okay? So, accelerating airflow, decreased pressure, decelerating, increasing in pressure. A stream tube is an imaginary tube made of streamlines. There is no flow into or out of the stream tube through the walls, as we said before, only a flow along the tube. With this concept, it is possible to visualize the airflow around an airfoil being within a tube made up of streamlines. So same as before. The tube in this case is the top of the streamlines that form the upper wall and the bottom. So it is the same as the tube we were seeing here. So, summary. At flow speeds of less than about 0.4 Mach, pressure changes will not affect air density. So the air doesn't compress that much that it increase or decrease air density at less than 0.4 Mach. So the principle of continuity, as we were saying before, air accelerates when the cross-sectional area of a streamline flow is reduced, and air decelerates when the cross-sectional area increases again. Bernoulli's theorem: if a streamline flow of air accelerates, its kinetic energy will increase and its static pressure will decrease. When air decelerates, the kinetic energy will decrease and the static pressure will increase again. So we need both theorems, and we have an aerodynamic force that's generated.